Hello class, today I'm going to show you how do nonlinear buckling analysis for a cylinder column. It is nonlinear, but the material is going to be elastic. Because I'm recording this video at home, so I'm using my tablet and free ANSYS available for students. So it is going to be a little bit slower than usual, but I'm doing my best to increase the quality. So basically we are going to have nonlinear behavior by having elastic materials. So let me open static structural. Okay, it's ready. The first one, let's check the materials. This is stainless steel, structural steel, and Young modulus is 200 gigapascal, so 2 times 10 power 11. Later we are going to need that. For geometry, I'm going to draw 1 meter bar with rectangular cross section, 1 centimeter by 2 centimeter cross section. The dimensions are going to be like that. So let's open space claim. For space claim, I need to have my keyboard. So let me turn on the tablet mode. So I will have access to my virtual keyboard. Okay. So space claim. Let's draw a line. It is going to be vertical. Now I want my keyboard. Let's undo it. So it is going to be from here up to 1000 millimeters. Okay, good enough. Now let's go and prepare it. I want a profile, this shape, rectangular. Let's edit this profile. So I'm looking for this. not here. I'm looking for 2 centimeter. So done. So it is 10 millimeter by 20 millimeter. Let's go back to our design, and now I need to select our bar and create it. Let's make sure, yeah, beams are ready. I'm going to get rid of this space claim. Let's open the model or mechanical design. Okay, it's ready. Geometry is okay. Cross section is also imported. Let's go with generate the mesh. We're happy with that one. Fix support at the bottom, and I'm looking for a force at top. It should be component, and the direction should be negative y direction. So let's put just -1. So -1. For solution, I'm looking for total deformation. If I open these stresses are off because the geometry is beam, so I need to include beam tools to read the stress or the other parts. Let's solve it. So this is going to be just static analysis of elastic material. Very easy, everything is straightforward. Let's see total deformation, very small deformation because the force was just -1 Newton. So we have no buckling, no nonlinear behavior, and stress is -5,000. Okay, now let's consider buckling. Let's minimize this. If you check here, we have eigenvalue buckling analysis using mechanical APDL solver. You are going to drag this over solution. I'm going to release. So it is going to read material, geometry, and model information directly copy to the second one. For the solution, she's going to import solution for the setup. Let's go back to the model and see what is happened here. As you can see here, now we have this new section in our tree, design tree, eigenvalue buckling. Okay, let's make sure everything is okay, refresh everything. Okay, pre-stress is ready. Analysis setting, automatically we have 2 modes, and definitely we are going to have 2 modes because it's a rectangular. And I'm going to need total deformation. What else we want to change? So let's add 2 total deformation. The first one is going to be for mode 1. The second one, let's select for mode 2. So 2 deformations. And that's it. Let me check once more. Haven't forget any detail. Okay, now let's, this is okay. Yeah, let's solve it. So we solve everything. Before showing you the results, I'm going to go back to my OneNote. As you remember, the formula for critical force was critical force for buckling was pi square Young modulus momentum of inertia divided by effective length square. Let's calculate for this case one of them. It is going to be pi square. The Young modulus was 200 times 10 power 9 gigapascal, 200 gigapascal. For the, let's calculate for one of the nodes. So it is going to be 1.1 centimeter power 3 times divided by 12. This is I, and length was 1 meter, so divided by 1 meter. If I calculate this one, it is going to be 3286 Newton. And for the other one, pi squared times 200 times 10 power 9 divided by 12 divided by 1, it is going to be around 820 something Newton. Now let's go back to our calculation. Let's see the total deformation for the one of the modes. It's 824. For the other one, 3295. For us, it was 3286. So it's very close, those load multipliers. And as you can see, let's check the, what else? We already know this. direct stress, total deformation for the other one, and these are the critical loads we have. Okay, now let's drag another one. I'm going to this time drag static, where are you? Static structural to the model. So what is my plan is using the material, geometry and model information, but this time I'm going to apply larger load. So I'm going to check if I going to have like a buckling around 824 Newton, or for the other mode 3000 something. Let's see. Let's refresh it. So everything is here. Now, as you can see, we have static structural number 2 here. Let's go and change analysis settings. I'm going to ask for 1000 seconds. And auto time stepping, I want to turn it on. I can use the numbers based on the sub steps or based on times. Let's go with time. For example, five seconds. The minimum time step 1 second, and the maximum time step 10 seconds. What else? And also I need to make sure large deflection is on, because we are going to have buckling. Otherwise ANSYS is not going to update stiffness matrix based on the geometry, because when we have large deflection, the stiffness matrix is going to be different. Okay, here let's add our support. So fix support at the bottom, and my load is going to be at the top, but this time much larger. Let's select the component, and it's going to be negative 1000. Oh, it's 10,000. So negative 1000 Newton. I intentionally selected 1000 because I want to be above 824 to see buckling. So it is negative, correct. I need like a perturbation to start this buckling because everything is like a vertical. So in order to start buckling process, I'm going to add another load again here, but it is going to be very small and trivial. So in X direction, and it is going to be 1 Newton. So very small load at X direction to create this buckling. So let me check the other force. As you can see here, for time 0 is 0 force, and then at time 1000 it is going to be negative 1000. So it's gradually increases. So because start from 0, we are not going to see any buckling, and then after passing 800 something 24, it is going to, we're supposed to see some buckling here. Okay, so let's add some solutions. Total deformation and beam tools. Yeah, that's it. Let's solve this one. Okay, we are lucky we have very small number of mesh and our column is very slender, very thin, so everything is much faster. Let's see deformation. I'm going to have, for example, 100 frames, and let's select 10 seconds, and force increases. Then check out here, 600, 700, 800 start buckling. Let me drag this. We need to see around 800. Now it start to buckling. Let's see once more. Yeah. So as you can see, our calculation for the eigenvalue buckling was correct. I'm just showing you one mode. You